1.1, we're going to analyze categorical data. Are you ready? Yes, you are. Let's do it. You guys, we live in a world full of data. Data, it's tomato. You guys are going to learn so much about how to look at data this year. It's going to be great. So, statistics. What is the definition of statistics? Everybody read it.
Is it science and art?
Wow, that was greatness. So yes, statistics is the science and art of collecting, analyzing, and drawing conclusions from data. So we will learn a lot this year about how to collect data correctly, how to analyze it appropriately, and how to draw conclusions from those particular that particular data that you have collected. Okay? So do you guys remember Joy, the lady that could smell Parkinson's? So she followed what we call the four-step method. The four-step method, all right, four-step process. And that involves these 4 steps. I'm not going to spend a ton of time going over these right now because we'll go through doing this a lot this year of doing all of these different steps. So we're going to ask questions, collect data, analyze, and then interpret.
Can you change the time?
All right, so, perfect. So, roller coasters. This data is about roller coasters. There are 6 roller coasters on this particular data table. You can see the roller coasters' names on the left side. Those are the individuals. An individual is a person, animal, or thing that is described by a set of data. And so this particular data table, the individuals are the roller coasters. Okay, so there's a question underneath the definition of individuals. It says who or what is the data describing? It's describing roller coasters. You don't have to give each individual name. It's just overall it's describing roller coasters. That's what this data is about. Okay, that is the individual. Now from there we will talk about what a variable is. You guys know what variables are, right? Yeah. So a variable is basically an attribute that could be different for each individual in the data set. And so we have 5 different variables in this particular data set. Type, height, design, speed, and duration. Those are the 5 variables in this particular data set. Most of the time your variables are going to be listed across the top of the table. Okay? So variables, what are the variables? Type, height, design, speed, and duration. Just so you guys know, sometimes the individuals' names are not listed, okay? Maybe it'll just have a number, or maybe it won't even say it. It'll just say there are 6 roller coasters in this data set, and then it'll just give you all the variables for those roller coasters, just so you know that that might be something you would experience very soon. All right, next up, categorical variables. So there are 2 types of variables that we're going to talk about, categorical and quantitative. Category, what does categorical sound like to you? A category, right? So a categorical variable is when I put a category for each individual. I give them a category that fits that variable. So for example, under type, it looks like there are categories of steel or wooden roller coaster. Under design, it looks like there are categories of sit-down, inverted, and wing coaster, whatever that is. So categorical variables, those are going to be the variables that give categories. We put the individual into categories. The other type is quantitative. What does quantitative sound like? A quantity. Very good. So a quantitative variable is going to be a variable that takes on a number value. And the reason is because we've either counted or measured something. Okay, usually it's a measurement. So height, we have measured how high the roller coaster is, and we've given it a value, a quantity. Speed, we've measured the speed of that roller coaster, and we've given it a quantity. Duration, we've measured how long is this coaster, and we've given it a quantity. Okay? So, what are the 2 types of variables? Categorical and quantitative. Very good. And whatever we are talking about for a particular data table, those are the individuals, and the information that we have about each individuals are the variables. Everybody feel pretty good about that? Perfect. Then you and your group have your first assignment. The American Statistical Association sponsors a web-based project called Census at School that collects data about primary and secondary school students using surveys. We use the site's random sampler to choose 40 U.S. high school students who completed the survey in a recent year. The table on the next slide and on your paper displays the data for the first 10 students chosen. The very far right column is basically the students had to answer this question. They had to answer, what do you most want to be in life? Rich, happy, famous, or healthy? So that's what that question was. That's tough. That's a tough one. So what you, yes, what you and your group need to do is you need to identify who are the individuals in this data set, what are the variables in this data set, and then classify each variable as categorical or quantitative. Now, guys, I do not expect you to write out every variable name and write categorical or quantitative next to it. You are more than welcome to just use a C or a Q for each of the variables and just label it on the table itself, okay? So I'm going to give you about 2 minutes to go through, tell me who the individuals are, and identify each of the variables as categorical or quantitative. Ready, go.
So categorical, like, I just think of quantitative. Grade level.
Is it measured? It's not measured. But is it
I wonder why.
No, I wouldn't mind. Thank you very much.
Who or what are the individuals that this data is talking about?
States.
It's not the states.
Students.
It's the students. It's the 40 students that that we picked, right? So the individuals are the students. As I said on the previous example, sometimes your individuals are not listed in the table. So the individuals here are just each of the rows is an individual, okay? I just don't have their names or anything labeled for them, okay? So one of the individuals is from South Carolina in grade 12, is a male, is 17 years old, January, all that. Like, that's one of the individuals. And that individual is a student that was in the survey. Does that make sense? Okay. So sometimes they'll be there, sometimes they won't. What are the variables that are shown in this data table? State, grade level, sex, age, all the things. Very good. It's basically everything across the top. So state is a variable. A lot of people don't say that one is a variable because it's the first one. That one is a variable because we just went ahead and started listing variables about each individual. Perfect. All right, here we go. Categorical. From left to right, which of the variables are categorical? State, grade level, sex, birth month, and status. Very good. So, did anyone think that grade level was actually quantitative? Yes. Yeah, that one's a little tricky there, right? Why? So you probably thought it was quantitative because it's a number. But think about it. Couldn't I just as easily say that this is a senior, freshman, senior, junior, senior? I could have just labeled them with a name. I'm just using a number for the label. So it's a label, a category. You're in the category of the 12th grade. You're in the category of the 9th grade. So just because it's a number doesn't automatically make it quantitative. Okay, it's whether or not you have measured something. I'm not really measuring anything. I'm just labeling them with their grade. Does that make better sense?
Yeah.
Perfect. All right, obviously you guys, the leftover ones are the quantitative ones. Age, height, and arm span. We have collected that data. We have measured how old you are in years, how tall you are, and your arm span. Everybody feel okay about this? Ish. All right. Perfect. What about zip code? What if I had put their zip code on here? Would that have been categorical or quantitative? What do you guys think? So zip code, is categorical because, again, just because it is a value, a number, doesn't make it quantitative. It's whether or not it's a label or not. Here is a picture. You don't have to draw this. Man, I'm so good. I'm such a good artist. All right. Did you know that when you're on the East Coast, your zip codes usually start with like 01 or 02 or 1 something when you're on the East Coast. And then as you go further over, what's Texas, obviously? We're like 7.5, 7.6, 7.8-ish, right? And then as you get over here, anybody know Beverly Hills, California? 90210. So as you go from east to west across the U.S., it goes from 0s to 9s. That's just a fun fact for you. Cool, right? Awesome. Okay. A distribution. A distribution is going to tell us what values are available and how many of each of those values. Frequency table. A frequency table shows us the number of individuals in each data value. So if you guys flip the page, you will see this little box that has all of these answers. These are the 40 students and their answers to that question of whether they'd like to be rich, famous, healthy, or happy. And we need to turn this into a frequency table. Again, a frequency table just shows the number of individuals in each data value. So, what do you think we should do? We should do some counting. We need to figure out how many of these 40 students said that they wanted to be famous. What'd you get? 7? Anybody else get 7? 7? 7? 7. All right. Happy. How many of these individuals said that they wanted to be happy? 21?
Yep.
Anybody else get 21?
I got 20.
You got 21? All right. Happy 21. Healthy. How many of them said they wanted to be healthy? 4. Very good. And rich. How many said they wanted to be rich? 8. Very good. Anybody know what would happen if I added those numbers up?
40.
Why would I get 40? Because there were 40 values. Do those add up to 40?
Yes.
Yes, they do. Very good. This is a frequency table. Do you guys have any questions on how to make a frequency table? This is too easy, bro. I thought this was AP stats.
I like this though.
You like this? You do?
Does it get harder?
Oh, for sure. Absolutely. Yeah. It's going to get way harder.
The test is going to be like...
Yeah.
Wait, is this the easiest?
Oh, for sure, this is the easiest unit. Absolutely.
When are we going to learn the hardest one?
The hardest unit of the year happens right before Christmas and then followed up very closely by the one right after Christmas. Fun. Yeah, Christmas is we have to have Christmas so we can break those two up. It's the only reason we have Christmas.
What are they about?
Well, I mean, I could tell you, but it would make no sense. A relative frequency table is going to show the proportion, fraction, decimal, or percent of the value out of the whole. It's how is this particular value related to the total, okay? So, for example, famous. How do you think we're going to figure out the relative frequency for famous?
7 divided by 40.
7 divided by 40. You got it. 7 divided by 40 is 0.175. That is the proportion. Very common, we will call it proportion, a decimal, a proportion. Now, what is 0.175 as a percent?
17.5%.
17.5%. And now you know why some of those questions were on that quiz yesterday. Because we will very often go from percent to decimal and back and forth. All right, guys, happy. 21 out of 40. What is that as a decimal?
0.525.
0.525. What is that as a percent?
52.5%.
52.5%. Let's go. All right. 4 out of 40. You can do that without a calculator.
10%.
That is 10% or 0.10. 10%. Very good. And then 8 out of 40 should also be pretty easy without a calculator. That is 20% or 0.2. Very good. Hey guys, what would I get if I added all those percentages up? I should get 100%. And what would I get if I add all the decimals up?
1.
I should get a 1. Because 1 is equivalent to 100%. If I put a decimal right here and I move that decimal 2 times to the right, I would get 100%, right? Very good. Do you guys have any questions about a relative? Yes.
For the fraction, if we can simplify it, do you want us to simplify it or leave it?
It does not actually matter to me.
Okay.
Because most of the time we are going to be using decimals and percentages. You can use a fraction, but we don't use them a lot except when we do a little bit of probability. But for the most part, we're going to turn those fractions into decimals anyway. Yep. All right, great question. Hey guys, why do you think we would want to use relative frequency instead of just the count or the frequency? Why is it better?
Give me it.
You get really large numbers or like.
Very good, very good.
Oh my god, that was so funny.
Easier to understand
What did you say?
large values. Okay. Why would it be better to know that 52.5% said they wanted to be happy as opposed to 21 said they wanted to be happy?
How many people are asking?
Exactly. So when I just give you the count, unless I give you the total, you don't really have like a perception of how, like, what is that a lot or is it not a lot? Right? If I just say, hey, I took a survey and 21 people said they wanted to be happy. Was that out of 1 million or what? Like, so a percent though, like everybody pretty well understands that. Okay. Here's another thing. We can compare distributions of different sizes. That is not writing, is it? Of different sizes. We can compare distributions of different sizes.
Tell me that video just in a story instead of trees. Do I know it? Should I say from the whole class?
I'm so glad this is a small class because I have plenty of desks to move you to. We can compare distributions of different sizes. All right, so here's what I mean by that. Do you guys know how many students go to McKinney Boyd High School?
3,000.
It's like 2,700 to be exact. So, about how many of those do you think are females? About half, right? So at McKinney Boyd High School, there's probably about, that's a very funny squiggly, there's probably about 1,350 females, okay? That's a lot of females, right? Do you guys know where Bonham is? Bonham High School, Bonham, Texas?
Yeah, like 2 hours.
So it's about an hour up, kind of that way-ish, right? It's a pretty small school. They have about 200 people in their whole high school. How many of those do you think are female?
100.
Probably about 100, right? There's probably about 100 females. Now, ladies and gentlemen, you are smart people. Which high school has more females walking around? McKinney Boyd has 1,350 females. Bonham only has 100 females. But is that helpful information if I want to know the distribution of females within the high school? Not really, right? Anytime I take a large population and compare it to a smaller population, I'm going to have more in the larger population just because there's more of them. So when I put it on a percentage basis, they are the same, about 50% each. This is the biggest, most statistical reason to use percentages, is so that you can compare across distributions. Does that make sense?
Yes.
Perfection. Moving right along. All right, bar charts. Have you guys ever seen a bar chart before in your life? Absolutely. Have you seen a pie graph? All right, perfect. I'm not going to spend a ton of time. This is a bar chart. Here's an example of a bar chart. Bar charts and pie graphs are used to display categorical variables. Categorical variables. This is just a specific example of high school graduate or not, or college graduate or bachelor's degree or whatever. But here's the thing. Do I have to put these bars in that order? Couldn't I put them in the other order if I wanted to? Couldn't I put them in alphabetical order if I just wanted to? I could, okay? Pie graph. There's a pie graph right there. What do pie graphs need to add up to if you're using a percentage? 100%. Very rarely, a pie graph will have counts or frequencies. Only way that that's okay is if you know the total number in the pie, okay? But most of the time, you're going to see it in percentages. Again, it is also for a categorical variable. Okay, this picks back up to where you guys can see it on your paper here. So, bar graphs and pie charts are categorical variable data display. Here is a bar chart, and we're going to compare males versus females and their favorite ice cream flavors. We've only got 3 choices here, so chocolate, strawberry, and vanilla. Who likes chocolate more? Males or females? Females. Who likes strawberry more? Females. Who likes vanilla more? Looks like females, doesn't it? Careful. How many females are in the data set?
22.
There's 12, 5, and 5. That's 22. How many males were in that data set?
8, 9.
Only 9. So we need to be careful because in this situation, there are far more females in the survey than there were males. If I put it on a relative scale, now look. Which gender likes vanilla more? It's actually males. Okay? So because I put it on a percentage where I can compare them, now the data looks different. That's why relative frequency is so important. Okay? Got it? Got it. Now, I'm not saying that you can't use frequencies, just counts. I'm not saying you can't. I'm just saying you got to be very careful when you're looking at the data to make sure that you don't have something like what we just saw. All right, cool. Let's look at this example right here. This is on the next page. A random sample of 200 children aged 9 to 17 from the United Kingdom was selected from an international website's online survey. The sex of each student was recorded, along with which superpower they would most like to have. You guys want superpowers? Might be fun. Which one do you think you would want? Invisibility, super strength, telepathy, flying, or freeze time? That's good. So the side-by-side bar chart shows the percent, so this is in percentage, by the way, of males and females who chose each superpower. So here's what I want you guys to do. In your groups, I want you to come up with 2 comparison statements of the distribution of superpower preferences for males and females. Just 2 comparison statements. Obviously, you can make a ton of comparisons, but I just want you to pick out 2. Any 2 that I want you to compare the males versus the females and their superpower preference. Got it? Ready, go! You can work with your groups. So, some brave soul some brave soul tell me one of your statements that your group came up with. Who's a brave soul? Let's go, brave soul.
Females love to fly.
Females love to fly more than males. Okay, so you guys noticed at the beginning that was not a comparison statement. Okay, but once they added more than males, then it was. In the back.
Men like invisibility more than women.
Men like invisibility more than women. Perfect. Jensen.
Men and women equally want to be invisible.
Perfect. Men and women equally want. Very good. Very good. Anybody else right here? Come on, Tyler.
Hey.
Oh, females prefer, or I said both genders prefer invisibility.
Comparing, link them, more than, less than, equal to each other, all the good things. Got it?
Got it.
All right, good talk. All right, next. Here is another way that we could display the same data. Notice now on the x-axis, I've got the superpower listed, excuse me, and the gender is color-coded. So now on the left side, I've got the females. On the right side is males. Why is this one better or not as good as the one before? What's this one good for?
It's easier to compare like males and females.
Okay, easier to compare males and females within each super strength. Okay, was that what? Yeah, perfect. The graph before is not bad. It's just that one really kind of makes us feel like we're looking at males versus males within their own and then females versus females. So this one kind of makes us a little bit easier for us to compare within the super strength. Okay. So one thing I do want to point out is a key. When you guys are making graphs, if you're going to use color coding or you're going to do something like that, please make sure you use a key. Never assume that the person looking at your graph knows what you mean or why you're using a different color or something like that. You can also use different like patterns if you want to. You can do like stripes or dots or whatever, or shade one in, leave the one blank. But just make sure you're always using a key. All right. It is tempting to replace the bars with pictures and use special 3D effects to make graphs that look more interesting. But please don't do that. Do not do it. Don't do it. I think there's blanks for you to write down. Don't do it. Don't do it. We do not want to do this. Why do you think this is a bad idea? Yeah, it's harder to read. And here's the other thing. It kind of makes it a little misleading. Okay, there are a lot of misleading graphs in this world. And so our eyes react to the area. So like this chocolate right here, the chocolate cone is really much taller and wider. So our eyes react to that area and makes it look like over-exaggerates how big chocolate is compared to the vanilla and the strawberry. And so we got to be careful with, it's called the area principle, and you want to be really careful with that. Okay? All right, so here's a couple of quick examples. Harris Interactive asked adults from several countries if they like to shop for new clothes. The percent of adults in the United States, England, and China who said that they like to shop for new clothes is shown in the table. Here's a clever graph of the data that uses pictures instead of bars. Why is this misleading?
Because China's flag is bigger than the United States flag.
Yeah, China is 80%, England is 55%, but because China's flag is wider, it makes it look way bigger than England. So again, the issue is that whole area principle. Okay, we want to make sure that each one has the same width. Okay, so this is misleading because the widths of the bars are. So again, this one is misleading because of the fact that the vertical scale does not start at 0. It overemphasizes the differences, and it's just a bad practice. Okay? What questions do you guys have? Perfect. Good job. You finished your first day of notes in AP Stats. Only 180 more to go.